Hi everyone. In this video, I'm going to introduce the idea of a 4-vector. So we've already seen an example of a 4-vector, which is position. What we've learned is that in a relativistic theory, when we talk about an event and its coordinates, we have 4 coordinates that we deal with. We have x, y, and z, our 3 spatial coordinates, but we also have time. So if we want to label the position, the space-time position of, for instance, an object or an event, we label it with t, x, y, and z. This is our first example of a 4-vector. Now recall the coordinates that this object or this event take on depends on the frame of reference. And we saw that, for instance, in the example of a boost, these position coordinates transform in a very well-defined way. So, for instance, if we have a boost in the x direction, we have some new coordinates, which we're labeling with primes, t prime, x prime, y prime, and z prime. And we transform them with this Lorentz transformation matrix, which looks like this. T. And there are similar Lorentz transformation matrices for different types of coordinate transformations or different types of boosts to different frames of reference. And so this is really nice because we can immediately find what the new coordinates are of an event if we go into a different frame of reference. 4-vectors are going to be objects that transform in this same way. So some other examples that we aren't going to talk too much about in this video, but just so you have an idea in the back of your mind, are going to be a 4-velocity and a 4-momentum. So just like how we have this 4-component object for position, now that we're in space-time, we're also going to have 4-component objects for velocity and momentum, called the 4-velocity and 4-momentum. So beyond simply the fact that now we have 4 of these components instead of 3, there's deeper meaning to the term 4-vector. So what is a 4-vector? Or I should say 4 vectors sort of in general. Well, they're all going to have 4 components, thus the name. But the more important defining factor is that they all are objects that transform in the exact same way as our position 4-vector transformed. So these all transform. And when I say transform, I mean if we're observing these objects from different reference frames. We know if some object is moving with some velocity, if you're in a different frame of reference, that velocity is going to look different. It could be at rest or it's going to be at rest in some frame, but then in another frame, it's going to be moving. So we know this velocity is going to change. And when I say transform, that's really what I'm talking about. So all 4 vectors are going to transform in the same way as position, which is to say with a Lorentz R transformation matrix. All right, so they're all going to be objects such that, so for example, consider 4-vector. I'm just going to call it A, just to give it a name. It's a 4-vector, so it has 4 components. We can label them as some time, and then some x, y, and z component. We don't, maybe t, x, y, and z, I could have just called it 0, 1, 2, and 3. But we're just differentiating between our four components. They're all going to transform. If we go to some different frame of reference, now I'm going to add little primes, again, to remind us that these are our new coordinates for this object in our new frame of reference. So these new components, again, we'll keep to that same example for a boost in X. We use the exact same matrix as we had up above for position, right? If it's the same transformation, then it's going to look mathematically identical. Those two ones. Okay, so we can have lots of these objects, which are called four vectors, and the thing that unifies them is they all transform in the exact same way as we move between different frames of reference. So these are going to be nice objects. We've learned in relativistic theories that scalars are our nicest objects. Again, those are the objects that don't transform at all. They're invariant when you transform between different frames of reference. So our space-time interval is one of these objects that we've seen, that it doesn't matter how, in what frame of reference you calculate it, it's going to take on the same value. These are sort of the next nicest things. They aren't scalars. They do transform. They do change, but they change in this very nice, well-defined way that isn't too hard to calculate. So these are four vectors are sort of our second best friends. Scalars are our first best friends. Four vectors are the next nicest objects. So one thing that we're going to want to do with four vectors to sort of turn them into our favorite object, the scalar, is by doing something known as a dot product, which is going to look very similar to the dot product that you're familiar with from your other physics classes, except now we have four objects, and there's going to be some pesky minus signs to keep track of. So given two four vectors, and I'll call them A and B, with components just like the ones I wrote for A above. The dot product between these two objects is given by, we multiply our first, sorry, that should be a B, our first components together, and then our time components, that is, and then we subtract out all of our spatial components. So this looks really similar to the dot product that you calculated before, where you're sort of multiplying the components together. But instead of just adding them all up, we have a minus sign attached to all of our spatial components. Again, this convention is going to be different if you're reading a general relativity textbook, where normally they subtract the minus sign with the time components. But up to a minus sign, it's the same thing. And what this does is this results in an object which is a Lorentz scalar. So the result is a Lorentz scalar, which means we can calculate this dot product in any frame of reference, and the result is the same, right? The components of these four vectors are going to be different in each frame of reference, but the result of this dot product is going to be the same, and that's going to be an incredibly useful fact. All right, well, that is four vectors and dot products. Thanks for listening.